let's take a look at an example relating to arc length, and here we'll be able to see that the equation that we come up with in terms of radians is a little bit simpler. Let's go ahead and look at this example. Let's do something relatively straightforward. Let's take a circle that has a radius of 4 centimeters, and let's determine what the length of a 90-degree arc is. So arc length is commonly symbolized by the value s, and if we want to figure out what the arc length of this circle is in degrees, okay, we have to go through and basically treat this as a ratio problem with the radius being 4 centimeters and do the fraction of the angle that we're looking at. So in this particular case, the circumference we know is 2 pi r, so the arc length will be 2 pi r times the fraction of the circle that we're dealing with. In this case, we have 90 degrees out of 360 degrees. And so the arc length here becomes 2 pi times 4 times 90 divided by 360. If we work this out, this gives us an arc length of 2 pi times 4 is 8. 8 divided by 4, since 90 over 360 is 1/4, will simply give us, again, an arc length of 2 pi centimeters. Okay. So that would be the arc length we would get with our measures in degrees. And obviously, if we had an uglier angle, we would end up with uglier results. For the radians version of this same formula, let's suppose that we have, again, a circle of radius 4 centimeters. And again, let's take and determine what the arc length here would be for this particular segment or this particular arc of the circle. Now, let's take a look at the formula for the circumference. Notice that the formula for circumference is 2 pi r. But one of the things you need to now start thinking about as you look at and do problems is the fact that 2 pi often represents an angle. In fact, 2 pi often represents a complete revolution around the circle. So in this particular case, what we're seeing is that the circumference of our circle is the complete revolution around the circle multiplied by the radius. So in radians, our arc length formula is that the arc length is equal to the radius times the angle. And again, this is true only when theta is measured in radians. And just as a check here, recall that if you look at the table we worked out previously, this 90-degree angle is an angle of pi over 2 radians. So if we were to plug these values into our arc length formula, S is equal to r theta. Our arc length would be our radius, r, which is 4 centimeters, times our angle, which is pi over 2 radians. And notice that this will result in an arc length of 2 pi centimeters, the same value. So working with radians turns out to be a little bit easier. It makes formulas much easier, and this is a relatively basic formula. This is a straightforward formula to work with, and not so complicated. We can look at more complicated formulas and see the same thing, though, that our formulas become easier to work with. Another thing we can do with angles and work with computations in a circle is to look at the areas of sectors. So suppose we wanted to determine the area of a sector. In terms of degrees, the sector area is going to be the area of the whole circle, which is pi r squared, times the fraction of the circle that we're dealing with. Okay? So this is going to be the central angle divided by 360 degrees, where this is our central angle, and r represents our radius. This is for working in degree mode. And so you can see that we have a step here where we have to basically convert our angle. In radians, it's not so bad, because again, if you look at the formula for area in general, this is the area of an entire circle, and again we see pi in here, and when we see pi, we should always in the back of our minds be thinking a little bit about the fact that we're talking about angles here. There's something angular going on here. And so with radians, when we start to work on sector areas in radians, the area turns out to be 1/2 r squared times theta, when theta is measured in radians. This is a much simpler formula to work with. If we are using angles measured in radians, we don't have to do any converting, we don't have to do any ratios here. It's simply a very straightforward result. So radians bring us to situations where we're much more able to do problems that are complicated when we look at things in terms of degrees, but when we use the more natural unit of angle measurement, the radian, things become simpler. Here's the work out of the textbook that will be assigned based on today's lesson.